Good afternoon, everyone. Thanks for coming to this talk. And big thanks to Ken, WJ, and Minkyun for organizing such a great conference. Everyone who approved the papers. My name is Omid Rafieian. I'm a faculty at Cornell Tech. And this is a joint work with Mohammad Rashid, who's a second-year PhD student at UW, who's done most of the heavy lifting in this project. I wish he was here. Sohail Ghili, who's at Yale. Presenting this paper has been quite eventful for unrelated reasons. The first time we presented this was Marketing Science last year. It was a couple of days after the 12-day bar in our industry. The second time we presented it was at UT Dallas conference, the day after. The day before, Ron and I were talking about the possibility of it, and the day after it happened, and I presented this paper. Last time I presented it was at Empirical Business School, but a few days before the ceasefire broke. And here we are now. We'll see what happens. I told people that I'm going to keep you posted on times I'm going to be presenting this paper. And also to my review team, if you want to stop this, you could just accept this paper. You don't have to go around and present this paper. So, yeah. So, as you can see from the title, it's about auctions and bandits, how they meet each other, and we want to kind of like see, like, we're going to do some sort of like empirical analysis. So, the empirical aspect of it is very important. But in the first few slides, I'm just going to tell you about auctions separately, and then bandits, and then the intersection of these two streams, and where kind of like our paper comes in. All right, so let's think of an allocation problem, and let's consider a seller who wants to sell an item to buyers with heterogeneous valuations. So here the seller designs a set of allocation and payment rules known as an auction, and the buyers bid given the auction rules and their own private valuation. Unsurprisingly, this problem has been extensively studied in the past economics literature, and there are lots of Nobel Prizes in economics that are awarded to people who have established nice theoretical properties here. So that's a very well-established problem. Then let's think of another sort of like allocation problem, bandits. And in this case, let's say you are an experimenter who could with multiple arms to pull. And the idea here is that each arm is associated with some reward that is drawn from a fixed but unknown distribution. That's the idea. So the experimenter needs to explore to learn these characteristics of the distribution, and it leads to the canonical exploration-exploitation phase. Again, unsurprisingly, this problem has been extensively studied too in computer science, operations research, econ, and so on and so on. And there is a host of algorithms with established regret bounds in this domain. The main difference with the auction side is that here, unlike buyers in the auction setting, these arms are not intelligent agents. And then there's a classical way to think about this problem. They don't have sort of like a strategic. Now, we want to look at this sort of like auctions meet bandits. So consider a seller now. This is the problem, and this is like we presented generally, but the example is advertising, and the data we have is an advertising. So the seller owns a sequence of items. You could think of a sequence of advertising slots, and they sell an uncertain event that can occur like with a certain probability, like clicks or conversions. This is what we are selling. Like in many cases, we are spending clicks or conversions. So that's why there is some sort of like uncertainty involved. So here's the sort of like very high level way of like how we can think of this like mechanism. Let's say there is this P, which is the allocation rule, and there is E, the expenditure or like payment rule that you have. There is this whole summation. I'm just going to talk about these things at a very high level. So there is this event probability for each A is a subscript for agent. So each agent that you have in this game, these are ads you could think of. There is this event probability of conversion, probability of click, something like that. There is this thing, there is the true value for that. Then there is this allocation function, which is like that's without lots of generality. Let's think of the theoretical revelation mechanism that they reveal their valuations. And there is this estimate that you as the auctioneer have of their conversion product. It's not necessarily the same as the event probability itself, the true value. And there is this payment function here. So when you sum over all the ads and time, it will be your overall objective, and you can think about like how to find optimal allocation and things like optimal auction basically here, or like whatever objective you have. But this is just to kind of like highlight the overall problem, and not something that we are going to exactly do, but it's just to highlight like there are ingredients. And I'm going to highlight two special cases that are again like I talked about in the first few slides. So here, if the event probability that you have here is known ex ante, this becomes like a classical auction problem. So basically, you know some dates, and you run an auction. Now, on the other side of it, if the payments are fixed, if there's no strategic interaction, it becomes a classical bandits problem. So this is kind of, these are both the special cases of this general problem. As for the general problem, there are a few theory papers on that, but not many empirical papers on it. Again, these like if you are knowledge and if you know some, definitely let us know. And our goal is to fill this gap by offering some empirical insights into this problem. All right, so let's see, when does this problem arise? Like, what are the situations where we have this auctions meet bandits problem?
Defer if it's appropriate, but if you go back one slide, I've always thought of an ad network selling opportunities to advertise. The advertiser places a message, the message influences the event probability.
Yeah.
And I'm not seeing it in the notation. Should I?
So it's in the notation in the sense that it's a fixed, let's say you have a campaign with a certain message that has a certain mu A, right? So now if you have within a campaign multiple like messages, we can have specific message like news specific to those like different messages. But for simplicity, again, like it's supposed to be a very sort of like simple form of this problem and like some of the ingredients of the problem. Let's think of it as like each like agent, each bidder that you have in your auction. All right, so for the like when a problem like this arises, basically like at a high level, based on what I shared in the previous slide, these are markets with fixed but unknown parameters that you need to learn. You need to explore the system to learn some of these things over time. So you could think of multi-sided platforms that face cold start problem as sort of like prime example of when this thing outflows. Let's say new advertisers entering ad auction, which is exactly going to be the setting we have here. Or you could think of a ride-sharing app. There are new drivers, the matching algorithm, a matching mechanism that you have. New drivers come, they have some certain characteristics that you need to learn. And these things matter for the final outcome of your matching algorithm. Now, our particular setting is a sponsored search advertising in an app store. This is the leading Android app store in a large Asian country. There are a large number of apps, over nearly 1 million apps, but 80,000 developers, and a total of 100 million users. It's keyword search advertising, and it is highly valued in these cases because for anything you can think of, you have so many apps. So this is very important to get some prominence. And the other ingredient of this market, which makes it really good for our problem, basically, is the rapid innovation in the app market. So you have a lot of entrants coming into these markets, and it leads to a severe cold start. So for this audience of Carl,
just a positioning question again, like Kent, if it's too early, let me know, but usually when we think about new advertisers, the standard assumption is literature is they're drawing a valuation from a distribution. All advertisers, like each time, every arrival of an advertiser will drive a new value from the value distribution. So here, what you're suggesting is advertiser valuations are stable, correct?
These are, here we are, like it's, or like in other words, it's separable from the probability of. So it's kind of like this is like full separability that we have.
Yes,
but it can allow for this to be sort of binary.
So literature typically allows the probability of click to be constant across the impressions, but if the values are drawn fresh from that distribution, every arrival, which would suggest there wouldn't be a cold start problem in the sense that a new advertiser enters, just draws a valuation from the known distribution.
From their
Known to the publisher distribution of advertiser valuations.
Right. But they know their own valuation, like
The
advertisers
advertiser
know
knows their
they
own
bid
valuation.
based on that, but auctioneer doesn't. So the auctioneer needs to kind of like rely on optimal, there's some form of contracting to get them reveal this sort of their private valuations.
The
So that's-
publisher knows the distribution value.
They know.
And so, ex ante to any arrival, the advertiser distribution is private information. Not known to the publisher, but again, at the next arrival, the advertiser draws a valuation.
From the distribution, yeah.
So there's nothing to learn.
No, the thing that is to learn is the conversion product. That is the thing, the auction value problem we're trying to learn.
Click throughs.
Yeah.
So
Basically,
not valuations.
the valuations are kind of like they are known to bidders, we reveal it in the auction.
Thanks for clarification.
So I think this, people like in this room know really well, but let's go over that like very quickly of like what is the setting. Let's say someone searches for games, this is the keyboard, there is a sponsored app, there is not known, like we want to show one app here in the sponsored position, we said it's important, and there's an organic ranking of apps. The way it's done is that you call for an auction here, it's a pay per install auction, second price. For this single slot you have here, there are 3 apps that let's say participating in this auction, they bid, they have this quality score, which is an estimate of their conversion probability, then you get quality adjusted bid, and you allocate it to the highest quality adjusted bid, in this case, this app E, and they pay, if an install happens, they pay the minimum amount that guarantees their winning position. So in this case, they will pay for each install that happens, and this is kind of how the app placement here occurs. So now you could see that this call back to Carl's question. I think, yeah, this is related to your question. So here, the quality score is the publisher's choice. This is the platform choice. And the challenge is when you don't have any past data about it. You have no idea what is the quality, what is basically the conversion rate of a new app. But if there is a no app, you can resolve it. All right, so the big question, the overarching question in our paper is what is the optimal level of exploration here to learn this qualities? What is the conversion rate? Now, the platform to essentially address this problem, they use Thomson sampling, and they use some because it came up in one I talked yesterday. Also, like this sort of prior posterior of beta Bernoulli. It uses beta Bernoulli of alpha parameter 1, beta parameter 9. It gives you a mean prior conversion rate of 110.1. And if a conversion happens, if an install happens, then we show the ad, you add 1 unit to alpha. If no conversion happens, you add 1 unit to beta. Here's an example. Let's say the platform starts for every ad who enter the market with 0.1 mean prior. And let's say here is like 2%, instead of 10% is 2%. So over time, as you allocate to this ad, you update, and as you can see here, it converges to the true value after a few impressions. So you could see that the choice of your prior, what you set as alpha beta, it controls the level of exploration. If I set a lower beta, I can basically, if I start from 50%, I will explore a lot more to converge the value. If I explore set a lower beta, it explores less.
Okay, so is it right to think that the quality score set by the platform affects both the allocation, so which bidder wins, and also the bidding strategy?
Excellent question. So it affects allocation by design. So this is like based on this type of show. But to the extent that my changing of the bid doesn't affect my quality score in the current period, it is going to be separable. So there is this separability assumption that has been like in this literature and ad auction, and we're going to use that. And the idea is that if you change your bid, you're not going to change your quality score at the moment. So that is
the reverse true. So as the platform adapts and quality scores, bids adapt to that.
Bids don't, because this, again, like there is a separability. You are bidding based on the value post conversion, And this capture, the quality score captures the probability of conversion. So it's kind of like it's a separability that you have here. And again, if you change your bid, you're not gaining any. So you kind of like can improve it. It's like you have this dominant strategy of not changing your bid. If that quality score changes in any form, that is not within your bid. That's also known as the concept of the squashing in this literature that kind of like which you can change your quality scores, get different revenue, but advertisers will not change their bidding strategy.
Actually, the bid does depend on the volume of revenue, CSV, and what they put on. You have multiple slots.
If you have multiple slots, it can depend on that. Here we have a single slot.
Oh, you're doing this one. Slot.
And if you have a budget constraint, again, it depends. It's going to take, there's going to get some level of it, but we are going to, again, like here, we don't have any students if we have enough budget.
So bid equals valuation, that's the
In this case, yes, and let's get to that, like we have like a slide there, but the high level idea is that the second price auction, singular slots, you could prove it, like it's basically you are invoking a weekly auction property, but that's gonna be, you're gonna have this, fruitful bidding as a proposal.
So just going back a little bit, I guess I'm very slow, but what's the problem here? So you're trying to, so you're saying that auctions are not optimal, but you don't know the quality score, and so let's do bandit, the person I don't know.
No, but what we're saying is that there are lots of entrants coming to the market, and we are running the second price auction. You just wanna know from which point you wanna start. We want to kind of like compare different options in terms of the level of exploration they have for the entrants. So if I explore more, and I will get to that in a slide, in a few slides, like what are the like benefits of and costs of kind of like exploring more or less. But the idea is that where to set this level of exploration at the keyboard level.
But do advertisers use them? Do we,
Advertisers.
not
here-
advertisers, I guess, Google. No, who's
Uh,
running the option, whether running the option, that's the option.
Most of them, they have the updating rule, some form of like bandits based updating pattern. So it's not like that your quality score remains fixed throughout. So you have here that we have a very clean version of bandit, which helps us.
Okay,
So it's not like they have Google data and you have to kind of like see how they kind of set those quality scores. But in general, there is some level of adaptiveness in how they kind of like update these quality scores. And where do you start when they want to explore? You want a very similar to exploration problem you find and it's again like this. You have like some of the new entrants, you want to kind of get a sense of like how they're there. But some of these, let's like we will get to some of the details and it becomes clear.
So is it true in a first price auction? That if you change the quality score, the often bid is valuation? I don't think so, right?
That's a very good point. I will get to that in my implication of the slide. Here it remains like within the second part, and it matters like when you get to the first part, especially regarding the credibility issue of the auction. So here it gets to the point of like you can change these prices, like this like 2020 economics paper where I would change. This is the idea that if you have the second price, you can actually play with these prices, but first price is a little bit different. We are kind of working on it, but it's kind of like not within this.
yeah, for lots of, so, if I remember correctly, bandits, all the properties of bandits hold under a lot of independence assumptions, so in auctions, everything depends on what other advertisers are doing.
Yeah.
And that's why I think there are problems with collusion working out pricing.
Not collusion, I mean,
But I
collusion.
don't know what happens in advertising, but I think
Right.
there must be something also there, right?
Right. So I'm gonna show you like how it differs from this separate auction problem. That's one thing I'm gonna show you. And to a large extent, a lot of it depends on this like lack of and this nice independence property you have in multi-round bandit. Here you have like the prices that are determined in the market.
Yeah.
So, and those matter, like those depend on how you explore these qualities. But just hold on, like we will get it. There are lots of slides so that we will get to all the details. All right, so on the exploration, like the big question that we want to kind of like get to, what is the impact of exploration? If you want to think about it from a bandit perspective, there are two accounts, like what is this exploration trade-off? You don't want to underexplore, you don't want to have a low prior mean, because it means that you might miss some really good opportunities. There are some really good entrants that come to the market, and you may miss on them. So it's like you underexplore, you never understand that they are high quality. On the other hand, if you overexplore, you might wastefully allocate a lot to low quality entrants. So that's kind of like the question of where to set this level of exploration is something with tensions, but this is the pure bandit perspective. What is new in the auction setting is that the prices are also affected by it. So essentially, by exploring more, you are making the market more competitive and more thicker, and it affects the prices. And in some sense, exploration can also increase competition and market thickness. That's the idea, and that's how these two problems depart from each other. So this is the key sort of like empirical question that we want to answer. Okay, what is the magnitude, both in terms of absolute terms and relative terms. So we want to see what is the contribution of this new element, new auction element here, relative to the bandit problem element. So here the data we have, it's impression level data from this app store over 6 months. Each impression is a sponsor's position for a keyword. Unique features, like one of them is using Thompson sampling. The other one is that we have the observed details about both winning and losing bidders. For those who have worked with auction data, that's a unique feature. Usually you don't have that. And we have timestamp, keyword specific information, all this like who this app will win, what is the conversion rate, how they what is the potential revenue per conversion, the revenue extracted, which depends on the install outcome, and so on and so on. These are things that we observe. We focus on the first week of data for our counterfactual analysis. And we use top 1,800 non-brand keywords that generate over 70% of all revenue from non-brand keywords. It gives us over 5.2 million impressions. Here's the summary statistics. Again, I'm going to just focus on two very specific stats that we have here. One is that total number of bidders. You see the distribution. So the mean is 38.2. And the total number of entrant bidders is 21.6. So a very large portion of like all these bidders that you have in your market are entrants. So that's the severity of this whole start problem, why it is very important to think about it.
Just a point of clarification, so you said this is an app store. So this is pure display advertising. There's no monetization through the sale or commission for this display ad, right? In this context.
In this context, like search address, like App Store search. Basically, you have one spot and people search, and you allocate that, and basically it is like let's say they extract revenue, second first option they extract revenue for the platform first app. So there is no sort of like commission because there is no one paid commission.
So it's not generalized second price option because it's one slot.
So generalized in the sense that you have this, one slot is not multiple slots, so in that sense it is not. There are some people who say that another notion of generalized second price option is the addition of quality support. In that sense, we have quality supports, but we have bonus. So that's a very important clarification. All right, so external exploration is a very important thing in our data. I will get to you, Olivia. We have high degree of exploration in our data. 80% of entrants at least get 100 impressions, and 20% of them get over 1,000 impressions. This is key in our counterfactual evaluation because we allocate enough to some of these entrants to know their conversion, have a good sense about it.
Feel free to interrupt it there, but how do you are entrants concentrated in certain markets, or should we think of it as just like constant entry in all of these markets?
There is a big chunk of it is that there is a constant entry in most of these markets. We have done it, but I don't have the top of my head like what is the degree of variation in terms of number of entrants across these markets. If you see this, you see quite a bit of variability across this is across keywords. This is across
keyword markets.
So for some of them, you don't have, like for example, like a min number of entrants is 3, and you see that it gets to 64, which is like huge. So you have quite a bit of variation in terms of number of entrants in the markets. We don't play with that variation.
If a bidder is targeting multiple keywords, it is separate.
It is separate. It's keyword specific. That's a very good question. All right, so this is how, like, one of the definitions we wanted to work with is market thickness. We define it as the ratio of the second highest quality adjusted bid to the highest quality adjusted bid. And this is a number between 0 to 1. The closer it is to 1, the top two are closer to each other, it's more competitive. The farther it's from 1, it's a like really like thin market where there's a huge gap between the first and second. You see quite a bit of variation here. The centrality here is around 0.6, 0.7. but you see even like some very thin markets here. Top quartile, we call it thick markets. Bottom quartile, we call it thin markets. Interquartile range, we call it medium markets. This distinction is important because I'm going to show you one model-free evidence from our data that is very telling for most of the things I'm going to tell you later in our more counterfactual type analysis. This is from our data. We look at these three different markets and we separate impressions into three categories. One is where the entrant wins the impression. The revenue share from cases the entrant wins the impression. The other one, entrant ends up in the second position. The third one is entrant ends up in the losing position. Like it doesn't matter for the revenue or efficiency of this market at all, but when they end up in the third position or worse. So one thing you see is that in these thin markets, entrant second plays a huge role in terms of in determining the total revenue from these markets. So it takes over 60% of the total share, which tells you that in thin markets, you put this like entrant right in the middle of these two, and you kind of extract more revenue from. So this is model free. We will see a very similar pattern as we do some of the counterfactual, but this is just to show you in the data with the exploration of point five. Now let's get to the empirical framework. This is the thing, this is a problem that we want to define. You have different types of second price auctions with different exploration strategies. So the one in the data was alpha is 1, beta is 9. You could play with beta and have different levels of exploration. So these are the counterfactuals we want to understand. So this is how we define the mechanism. The goal is to estimate market outcomes under any Thompson sampling second price auction. The two key outcomes we focus on, like in the long tradition of auction theory literature, is efficiency and revenue. There's like revenue efficiency trade-off in auction theory. It's been very prominent, and we kind of like speak to that. Efficiency, think of it as like the total surplus shared between advertisers and the ad net for the auctioneer. And revenue is the amount that the auctioneer extracts. So what are the ingredients here? The Y here is the conversion outcome. V is the valuation. V times Y, that a conversion happens, it determines your total surplus. And this guy here, which is like pretty ugly looking, this is the second price payment in these auctions. So basically, if you look at this, we get to this remark that if you have advertisers' private valuations for conversion, and if you have conversion rates, these are sufficient policy invariant primitives that you need to conduct all these counterfactuals. That's the idea. So we want to get these. So we face challenges. The first challenge is that to get all these conversion rates, we need enough randomization. Remember that distribution I showed you, even for entrants, we have quite a bit of variation, which is, and this randomization, built-in randomization helps us. We need a strategic behavior from a structural sense to invert these bidding behavior and get their valuation. If you have, let's say, full randomization, there is no strategic behavior. Everyone bids reserve price. Here, you need to maintain some level of sort of like a strategic behavior, which in our case, we have a lot of it because it's a second price auction. That entrant part plays just a tiny role in this market. So again, it allows us to invert these bids, get the product valuations. The last part is we want to isolate the contribution of the auction environment, like this addition of auction to the bandits alone problem, I think I mentioned earlier to you. And for this, we compare this efficiency maximizing to revenue maximizing price. We will talk about it in more detail, like why efficiency maximization reduces to a weighted bandit problem, which is bandit only, and the revenue one is the one that is kind of like it gives us sort of difference.
So coming back to Yifeng's question about bids and valuations. So the idea is here you're inverting a bid to back out the valuation. Is that inversion function embed the quality score? Because if so, one would think that changing the quality score would change the bid. Holding valuation first.
In this case, we have a proposition that we like use a lot of things that have been used in the past, that truthful bidding, if you have the separability assumption that you're changing the bid doesn't affect your quality score, then you bid your true valuation.
So really you're not doing inversion, you're just saying bid, well, once you do it, just simplifies the examples.
Yeah. This is the part where kind of like we could call it a structural model, but it's a structural model which is just like immediately you get the number from the data. So this is probably the simplest. We talked about the structural models over the past, from yesterday and today. So this is the simplest you can imagine. But if we call it,
Where's this one as well?
sorry,
Where's this one as well?
whatever you want to call it, like you can't be calling it.
I mean, it's fairly standard. Yeah.
Right.
I call it the goalie transform.
Yeah. All right. So
That's not the goal in L.
let's see like what we do here. So here is kind of like, oh, sure.
Is it still true that bidding evaluation is the optimal strategy? The advertisers know the publisher is learning for over time.
Excellent question. The answer is yes, if they are static bidders. And I'm gonna get to that in one slide. If they're dynamic, no. But sorry,
What do you mean by that?
give me one slide. I have a full slide for you on this. And it's a very important one. So here is for conversion rates. I think this one probably no one disagrees with me. We just make an assumption that conversion rates remain fixed over time. We need some quantity to learn. So there needs to be something that is fixed that we are learning. So we can also like put it and make it time varying and like estimate it, but this is just the simplest form of it. But most of the in practice people are doing it. And we use a sample analog estimator. We have enough randomization, use a sample analog. You could run some alternatives based on inverse propensities for adjustment and so on and so forth. Nothing changes. Now to this question. This is the most critical part. We make an assumption, which you can, I think, when you can shout at me, then I make that assumption. The bidders choose their bids to maximize their repair to alleviate each, right? So now let's think about how reasonable this assumption is. We didn't want to make this assumption. We looked at the data, we saw that this assumption is reasonable. And let me kind of give you a very clear dynamic account. Why if you are a dynamic bidder, your bidding decision is not a truth table. If you know they are exploring. So basically I see an entrant come to the market, it inflates my price. I think I'm going to go out of the market for a few periods. Entrant quality is realized. The entrant is going like the overall value goes down. I come back to the market, I get the high information on rent I was getting. So we wanted to see if we see that in the data, we run some simple reduced form analysis. One is that we regress bid on lag bid and lag cost per click. If there is a shock in cost per click, if my cost per click increases, I need to change. If this account I told you is what's going on in the data, I would change my bid in the current period. They don't. In the OLS one, and also we do this, we instrumented with the timing of bench. So that's exogenous. You use it as an exogenous shift there of the cost per click in the previous period, still we find no association. But
one reason I think this might be really good assumption is most, I'm guessing the site uses a campaign bidding tool, campaign level bidding tool.
they don't, but many do. So in this one, they don't. But
So
so
with the campaign level bidding tool, there's not opportunity to react.
yeah. That has a different for if you have algorithmic bidding, which is kind of one of the future extensions. If you have algorithmic bidding, it creates some really interesting dynamics that you are not speaking to in this paper. But part of the reason is that they didn't have all these algorithmic bidding tools. All right, so then under this assumption, we get this proposition that many of you mentioned that truth telling will become the property of assumption. So if I enforce this static bidding and I have the separability of quality scores and bids, it will bid truthfully. So this estimation becomes very simple. You could call it a structural, you could call it like whatever Ali said, like, however you want to call it. Boni-Mela estimation. That's excellent. So if you have these two, you can simulate the counterfactual outcomes under different exploration strategies. So this is a very long one. I'm not going to go into detail, but I think that the idea is clear. So you run this Thompson, you start with Thompson sampling, you allocate these ads, you have the valuations, you have the conversion rates, everything just follow through. Now, this one, how do we get the role of auction, isolate the role of auction component? So basically, if you have counterfactual policy evaluation, you can use any sort of prior, measure these market outcomes, efficiency and revenue, right? So now, under each objective, we can get the optimal prior. What we make here is that maximizing efficiency reduces this weighted bandit problem. Why is that? Because you can enforce some direct correlation principle, they will be truthfully, you get the values, and this becomes a weighted bandit problem. So this is here, you don't have that strategic like pricing part that comes into play when you do revenue maximization. That's a key part to kind of like decompose these things. So one is efficiency maximization, pure bandit problem. The other one is revenue maximization through choice of prior. That is kind of like the difference will tell us lots of things about how these two problems depart from each other. Now I will get to the empirical results, and I have 12 minutes. Right?
Yep.
12 minutes.
Yep.
So we vary the beta parameter. So we don't do it with alpha. It's kind of like partly because of the variance we wanted to kind of like update more quickly. So we have alpha, we set it at alpha to 1, we change beta. We don't make it more exploratory than what we have in the data. There's a specific reason for it. We said there's an assumption of a static billing. We don't know whether it holds if we kind of change the exploration to like a sci-fi level. So we don't want to say things that are kind of like crazy. So we stay within sort of like less exploratory policies for the data. So this is here the efficiency graph. This is revenue graph. On the efficiency side, it is maximized around mean prior of 0.002, 0.2%, which is fairly close to what we see actually as the average conversion rate of entrance in the data. So if you are looking for the efficiency maximization, that's kind of like you do some modest level of exploration, not too much exploration. But on the revenue side, what happens is that the most exploratory policy, which is our data, this red star that we have is the actual data value we have. This thing here is the revenue optimal product, so the most exploratory. Now it might be you might be dissatisfied with this not kind of continuing to like 0.2, 0.3, and so on and so forth. Again, the reason is just we want to be like more counterfactually valid here. So this is the analysis we do here. Now, this kind of highlights the role of market thickness, new piece in this problem, and we move from 0.002 to 0.1 as the optimal product. Now let's see it a little more sort of like clearly. Ali talked a lot about Pareto frontiers. Here's a Pareto frontier of efficiency and revenue, which is like very well known in general in auction theory. So what we see is that this is the efficiency optimal value. And from here to the revenue optimal one, we get 0.3 million, and these are all normalized increase. This is both in relative terms and absolute terms a huge change. So these two problems are markedly different from each other. And this is kind of like if I want to have one takeaway from this paper, is this. So this is these two problems are very different from each other. Again.
Have you considered using a minimum or adjusting the reservation price to?
No, it's a very good question. They have a reservation price. We went with that reservation price that they have.
Do you think it might be a tool to get close to the efficiency?
It might, so it's a little bit different. The problem, like for the reserve price, kind of you set it at the market level if you are kind of exploring. Here we are exploring at the market advertiser level with what we have. It's an interesting extension. That's what I can say. We don't do it, but it's an interesting one to try.
But let me just push you. So why do you have to set that at the market level? Couldn't you discriminate between advertisers?
No. For the reserve price,
Yeah.
usually they don't. So like in these auctions, you could do that. No, you could. I mean, it could kind of like even go to the fair specs. You have all the valuation.
Yeah.
You can go to the highest one. Say, okay, you pay me this amount, or I don't allocate anything to you. But realistically, they set one reserve price for each keyword, and everyone operates based on that. Usually, even like they set one reserve price per keyword. Here we are not changing this because that's a separate problem. All right. So now, in terms of underlying mechanism, this is what I showed you earlier in terms of model-free evidence. This is the efficiency optimal. This is this y-axis revenue. This is efficiency optimal prior. This is revenue optimal prior. And what the thing you see that happens is that the share of entrant in the second position increases drastically. So the gain you get is by just putting the entrant in the second position, increasing the prices, making markets stickier, extracting more revenue.
Going back to Ken's question, if you put the entrant in the second position, it's as if you're raising the price, right? So you get the same result,
That's why I'm like, the way it works in some ways is similar. It's saying that you are setting the reserve price for these markets separately. But there are many ingredients, I'd be happy to chat offline about this, that are different. But in terms of the functionality of it, the way it works here, this exploration, is very much the same as like setting reserve prices so that you get good amount of revenue. I will show you something on upper confidence bound algorithm, and it's very similar to that. It's even like it remains fixed, it's not probabilistic. So we will see some results in that sense. Second mechanism that happens here is that if you look at this, the inefficient allocator price you pay for more exploration is that you have more inefficient allocation. So you allocate to the wrong ad more often. So that's what happens. So you distort efficiency, you gain some revenue. And this is kind of like in the calculus of it, it's really profitable for a platform. One thing I need to highlight many times whenever I'm presenting this is that point one, the most exploratory policy is our data. This is not counterfactual. So this is really what's observed with data. We are not going to about things in our counterfactual that is that favors our conclusion. Now we look at the heterogeneity across markets. You see a very stark contrast between thin markets and thick markets. In thin markets, again, this effect, this sort of second price bump, is more prominent. But then you go to thick markets, actually the efficiency optimizing prior does better in terms of revenue than the revenue optimum prior. So 0.002 does a better job overall in thick markets. Why? Because these prices are reasonably competitive to begin with, so you don't want to kind of inefficiently allocate. This gives us some idea that maybe we can customize these priors across markets. Very similar to customization of reserve prices that Ken mentioned. And this is what we get, this efficiency revenue trade-off. The blue one is for uniform exploratory policies. And the green ones, these are customized priors that we set. It's very rare. I've worked on this like multi-objective optimization problems. Very rare to get like such a nice concave pattern on the Pareto frontier. But you can see that you can push this Pareto frontier a lot by customizing your prior, getting some points that actually dominates all these, like let's say for example on the thick market side, this point around here, it can dominate pretty much everything you have, right? So this is, or like very close in terms of revenue, but so much better in terms of efficiency. And it follows through for other like medium markets and thin markets, and then thick markets. So this is one of the insights. The other one is that we say, okay, why don't we use upper confidence bound? Thompson sampling was forced on us because of the data. So that's kind of like we tried different Thompson sampling. The two algorithms are different in very interesting ways. Thompson sampling draws probabilistic mean from distribution. Upper confidence bound stops at some point where the upper confidence is lower than the lower confidence of the top price. So one thing we see here is that UCB dominates Thompson sampling, and it is, if you want to see the reason, Thompson sampling, because it's probabilistic, it continues allocating inefficiently. It's kind of like, let's say it gets to a very good price, but it still continues kind of updating the conversion rate. Upper confidence bound gets to a very good price. It doesn't, it's just kind of like extract this price. So, and UCB is kind of like interesting in another sense that even if you kind of like fully relax and allow for like fully forward-looking bidders, you could enforce some version of UCB in a dynamic auction that is incentive compatible. Happy to chat about that too, but this is kind of like one because there is again like the lack of probabilistic behavior. It reduces the ability of bidders to kind of gain this sort of like quality scoring process. If we do something with budgets, we then have budget constraints. Here we put some budget constraints in the sense that the max daily budget they spend is their set budget, right? So this is kind of like what we use. Results don't change so much. So it's largely the same as what we had. Of course, some of the things slightly kind of like the quantity magnitudes change. Okay, to conclude with some of the managerial implications, the key thing we wanted to say is that this auction component is very important. It's joint auction bandit problem. So thinking about this, the prices are determined through the market endogenously. It's very important, and it changes most of the insights you have. Like maybe like you are a manager, you say, okay, my conversion probability is around 0.2%. So let's set the exploration at 2.2%. Not a good idea. You can actually get more revenue by increasing the level of exploration. So exploration is a device to increase market thickness. For policymakers and regulators, Carl asked this question earlier about first price, second price differences. Here it kind of like speaks to this credibility, like an auction trilemma type question. Like if you have a second price auction that has like, there has been this sort of like speculation that first price winners, they are paying a large amount and the platforms are very opaque in terms of like not communicating how you got to this price. This is something that happens here. So increased transparency in these auctions, it could be a solution. We don't talk a lot about it in the paper other than like this manager application, but these are really interesting questions for future. One thing I want to say is that I talked about this particular market being really like with innovation, like the rapid innovation here. In general, we have rapid innovation in advertising markets with Gen AI. We have lots of entrants, and this full star problem is relevant in most of the advertising markets.
Next step kind of question. How do these findings, I mean, they're general findings, but how are they moderated by the quality score or how much washing is done?
You could maybe tried actually one thing which maybe we didn't put in the paper, the combination of squashing and exploration, you get better results. So it's kind of like you can actually increase this.
So it enhances.
Yeah. But it's a device which is kind of like, I think the opaqueness of the squashing is not something many of the platforms want to do. This is kind of like a little bit more.
And does it affect the trade-off? I can imagine it would because.
The trade-off?
The revenue.
Yes, it does. Yeah. So finally, again, main finding is this sort of like auction bandit solution differs markedly from the standard bandit setting. We quantify the gains from exploration through market thickness channel. We talked about customization and how much it is helpful in terms of like even like improving both revenue and efficiency outcomes. And we talk about the sort of like UCB-based dominating Thompson sampling. For future research, one great question that came up is like auto bidding, algorithmic bidding. It's a very sort of interesting question to see how these two interact with each other. Here we didn't have like much of it, and we didn't find evidence for them doing some sort of budget consideration. And another thing I would love to do, but I mean, we couldn't force the company to do that, is to actually implement more exploratory policies to see what happens. We didn't do it because of the counterfactual validity concern. It would be a very nice future work to just document those things. Thank you very much for all the questions, and I look forward to answering them.
Okay. Are you okay?
I'm almost,
You're not asking questions.
I'm very shocked that.
Yeah, I see. Yes.
I thought we're discussing truthfulness now. Good afternoon, everyone. So if we haven't met, I'm Ron, and it's nice to meet you, and I want to thank the organizers for inviting me to discuss Omid's paper. So I want to recommend first of all you read the paper. It's very, very clear. Okay, a bit long, so there's only one comment, but you can kind of understand what's going on in there. And it's interesting that most of the questions here were about the auction. I'm actually going to focus more on the bandits. But I think this is actually some part of the more interesting issue. So I saw there's a lot of knowledge here about ad auction, but I'm going to do a very brief introduction to ad auctions, okay, and why we have these quality scores and what their goal is. So imagine I have one link, okay, and I have two bidders, 1 and 2, and they value, let's say, selling the app in V1 and V2. It's a second price auction, so in equilibrium, they should tell me their valuation, and I rank it. And the top link goes to player 1 because it has a higher valuation. But if they actually sell the app, they would pay V2. So this is like classic second price auction I would like to do. The problem is usually in those ad auctions, you don't know if someone is going to buy. Okay, so I know how much I'm going to bid, but I don't know if someone is going to buy. So and I'm only going to pay if I make a sale. So I need to start calculating what is my probability of purchase or not purchase, etc. Okay. So the solution that is usually implemented is what we would call a quality score. Okay. So now the auction works on scores, not on bids. Okay. So you take the bid. I'm going to assume they're truthful. So I assume the bidders told me their valuation. I'm going to multiply it by the actual true probability of conversion, in this case, mu1 and mu2, okay? I'm going to rank them by the scores. So the one with the highest score, I'll point this way, by the score is going to rank higher. And there's a way to adjust the payment once we do that, okay? Now, why do we do that? It removes from the bidder the kind of burden of knowing what is the probability of purchase. So it kind of eliminates, the math is relatively cute, eliminates the need to know, are they going to purchase or not? Just tell me how much is a sale worth for you. We're going to do that, okay? And then the auction becomes truthful and it's all good. But what happens when we have new players? When we have new players or new app sellers, we don't know exactly their probability of purchase. Even they don't know it, right? And we need to put an estimate. So this is why I have a hat there on YouTube. I mean, it becomes a cold start problem. Okay, so this is kind of the beginning of this paper that says we have an app store, a lot of new entrants. We need to learn what they're doing, okay? And then once we need to learn something, right, and not just kind of have an incentive compatible mechanism. So we want to learn the unknown quality score, but we also need to sell these ads while we're doing that. So our goal is not just to learn those things, right? So we want to also maximize the revenue. And it kind of sounds like a multi-armed bandit setup, okay? And what do I say kind of sounds like? Because multi-armed bandits has a lot of specific definitions that we need to hold, okay? And this sounds like it, right? So in order to position it as a multi-armed bandit setup, we need to say what is the auction, sorry, what is the action that we're going to try to exploit and explore, and also what is the revenue, okay? So in a classic multi-armed bandit setup, right, we either say sometimes we exploit, we're going to choose the action that is not profit maximizing for us to learn something. Sometimes we're going to explore, which means we're going to choose what we currently believe is the most profit maximizing action, okay? What is not a multi-armed bandit in this case, right? So first of all, what is the action? The action is who wins the ad auction, okay? Either number one wins, number two wins. Number one wins, number two wins. Profit maximizing means I'm going to give the link, the one which I predict is going to have the highest click-through rate times bid. Exploration means I'm going to give the link to someone else, okay? So this is what I want to do. I want to randomize who gets the winning bid, okay? Problem is, because of these quality scores and those beliefs and those learnings, if they win and they make a sale, how much we're going to pay is going to depend what happened to the second one, and that varies, okay? And that's already not the multi-armed bandit in the classic sense. In the classic sense, the return of the rewards from opening one of those boxes in Weitzman's model, etc., should remain the same and not depending on what happened to the other one, okay? The other weird thing is that if sometimes I allocate to player one, I might learn something about player two, which is also something that shouldn't usually happen in multi-armed. So the question here, as I see it, at least in the papers a little bit, we got this data, they allocated things through Thompson sampling. How does it affect the revenue of the auction, the efficiency of the auction and the revenue from the auction? Because Thompson sampling is guaranteed asymptotically to be revenue maximizing in ad hoc, not in ad auctions, in general multi-armed bandit settings, but this is not a classic multi-armed bandit, okay? So the research questions kind of that the paper presents, okay, is first of all, for Thompson sampling, right, how does the prior mu2 affect revenue and efficiency, okay? And the second one is, does another heuristic or other things I can do can perform better? So I'm going to go back a second and explain, first of all, Thompson sampling, because I think a lot of it hinges here on what Thompson sampling does. You can think of Thompson sampling saying, I have a distribution on this mu2, this quality score. It's a posterior distribution. I draw a number from it, okay? So if mu2 is a big variance, I will draw very high and very low numbers. If mu2 is a low variance, I will draw very close to the predicted mean. The mean is higher, I draw high numbers. If the mean is lower, I draw low numbers. I run this auction, but now a weird thing happens. If I happened that player two was ranked second, I'm actually not going to learn anything about player two, because they're never going to win, they're never going to sell, etc. If it happens that player two wins the auction, then I can update basically my belief about mu2, and this is how Thompson sampling operates, okay? So it is stochastic, and it matters for two things. What is the mean and what is the variance of my belief? This is important for my discussion. So given those research questions, what the paper does basically is it says, we take this data set, okay? In this data set, we're making an assumption. That was a lot of discussion here, and I think Omid answers very clearly what I think it holds. That the values that are C are kind of static and basically represent what the bidders actually believe their valuation, right? I saw the actual probabilities of allocation and I see the actual sales. So I have the structural parameters. I can simulate the game and I can change the prior, okay? Once I change the prior, I change for new entrants. Do I believe they start with a basically high conversion rate or a low one? They start actually in reality pretty high. And then maybe over time they convert lower, they converge higher. And the main result of the paper, it says that basically kind of there's a trade-off between efficiency of the auction, which means do I allocate the ad to the one with the highest valuation versus revenue, okay? So when I start with a prior mean low, okay, which kind of means actually new entrants, I think they're not gonna be very good and probably they're never gonna win the auction with very, very low probability. The auction is very, very efficient, so the highest valuation bidders win. But actually, if I wanna maximize my revenue, I should give the entrants a big boost at the beginning, and basically they're gonna kind of slowly fall down to the right places, but this will maximize the revenue. Which by itself is interesting because I don't know if there's a lot of thought given to how do you start the multi-arm bandits to converge and what is the implication in the long run. This is most of the literature I know about multi-arm bandits. We just start with some prior conversion. Okay. Now, I think this is very interesting to see, and Omid explained clearly what is the mechanism. Okay. So the mechanism is on revenue, right? That the low prior, as I said, mostly the entrants never win and they affect nothing. And with a high prior, the entrants often come in the second place and they just push the revenue higher from the highest bidder, okay? For efficiency, it's actually not a big difference, but basically when you have a higher prior, of course, sometimes those entrants that are pretty bad maybe win the auction condition. Okay. So there's still more results, actually. So one comment I have, and I think they're kind of very new and very interesting that we show, and Omid went through them visually. I think the fact that different exploration can be customized to thickness and thin markets and actually affects dramatically how the revenue operates is something I haven't seen before. This is because of this auction setup, because the thickness and thinness of the market affects actually the revenues. I think this actually should be emphasized in the paper. And the other thing, which is kind of interesting, this platform chose to implement Thompson sampling, but actually in reality, upper confidence bound performs better. And I'm going to talk about it in a minute. Okay, so I have a few thoughts. And this is kind of a few things about the implementation maybe of the paper, but maybe other things to think. So the first thing is that I didn't really see a lot in the paper. I don't think Omid discussed much is the impact of the organic links. And I don't know if they're in the simulation or not. Okay. Do you just simulate the sponsored part or organic? The reason I mentioned the organic part is that the actual truthful bid is not your valuation for a sale. It's your valuation for a sale minus the outside offer from a sale from the organic, which means if you're a player that is ranked very high for organic, you should be pretty low for the ads. If you're ranked really low for organic, you should maybe bid very high, okay? And that's affecting the simulation and many things, and I recommend looking at that. A second thing is that the paper talks about the multi-round bandit, but I said in the multi-round bandit, you need, first of all, to give the reward signal back. But here we're only getting, do you get a sale or not? This is not the reward. The reward is how much money I made from the auction. That depends, did I get a sale, what is the valuation, and how much the second one paid, okay? And the second thing is Thompson sampling, what it should do is it should affect, as I said, the action is who wins the auction. The Thompson sampling should directly affect who wins the auction. When you just change mu, you're implicitly affecting who wins the auction, but the auction is determined by mu times v. And v changes both the mean and the variance of those scores. So my recommendation is draw directly from the scores in the Thompson sampling. I think the revenue will increase. Okay, currently, they're just doing mu updating. But actually, if you have a high V or a low V, it means your probability of Thompson sampling draws should be different depending on your V, okay? Now, given all of this stuff and given the breakdown of a few multi-round bandit assumptions, one thing I'm asking is maybe you should go to reinforcement learning, which is kind of a generalization, let's call it, of a multi-round bandit. Because what you want to bring in when there's a revenue, you don't want to bring in this binary signal that says there was a sale, there wasn't a sale. You want to bring in the signal that says, or the reward signal says the profit was 20 cents or 70 cents, etc. And learn it, kind of let it learn in a very non-parametric way how it works. And again, my prediction that if you use something like a Q-learning or other reinforcement learning agents to do the exploration exploitation, you might reach even better performance there, but it won't be as clean as the multi-round bandit. What about priors to test? So they focus on changing the mean, but also the variance really matters. So beta 1.9, which is what used as an example, and beta 100, 900 has the same mean, but very, very different variance, and that will highly affect exploration. And I think it's interesting to look at that. In the last minute I have, I want to talk a little bit about upper confidence bound. So you can think of upper confidence bound as just taking the mean plus a term to add exploration. But the method that the paper here kind of looked at and implemented is what's called UCB1. It's like the basic method of upper confidence bound. But you actually want to add the belief about the variance there. You want to look at it like a confidence interval. So this is called upper confidence bound tune. And this will go closer to changing both the variance and the mean in the Thompson sampler. I think it's kind of very, very interesting to see that this method that is more deterministic also lets us learn more, but also does that. So just to summarize, okay, I think the paper does a very good job explaining why a multi-round bandit solution, which was implemented, can kind of help solve also problems, okay? The data, of course, is very, very cool, right? Like you very rarely see won the auction, didn't win the auction, how things operate, etc. And something I haven't seen, but again, I'm not that specific about multi-round bandit literature. How do you start the learning really, really matters here for the revenue and efficiency, like these priors, although it seems like, yeah, just choose an uninformative prior and let them converge because of this interaction with the auctions. And I think this is kind of a very nice thing that this paper introduces that will probably affect a lot of what other people do. That is it. Thank you very much, everyone.
All right, so thank you very much for your comments. It's really useful. A few things to clarify. We take the organic rankings as given, so we are not assuming that it will change cascading for or less for the responsive ones. It's an interesting extension. I don't know. I think we have data in place. From the reward signal, I think one of the things you say have to much of this sort of like ad option literature is kind of like operates on this separability assumption. So here, if we draw from this like full profit, it will shift the bidding. Now we have this truthfulness property that we can kind of like prove it. And I think part of the reason is kind of like there was recent articles on Monroe and like this has been like very useful for each platform and just get the user specific, whether there's separation of user side, advertiser side through the auction, you get it, and the other one from the other side. It's an interesting extension. It's going to be very more complicated. And for the variance of Thompson sampling, we did that. So we didn't put it in the paper. The issue is that it's going to be more inefficient. So updating doesn't happen as frequently. So you put that person like today on instruct and you keep allocating to them even if they are.
I think the paper doesn't mention much about the speed of updating, and I think that's actually very important to include because that might be more important than efficiency. Like how quickly do you know and learn those things?
And lastly, to your point, it's a limitation. And generally, you don't see much in the bandit literature about the choice of prior. So most of the things are regret bound and they are kind of like independent of the prior you sent. Here we try to kind of like bring a fine example. So it's kind of like what I did. Thank you very much.